Now that we have enough background of multivariable functions, about how they behave, domains of multivariable functions, their limits, properties of continuity, things like this, we're now equipped to dive into the topic of partial derivatives. And to understand partial derivatives, it helps to recall the derivation for the limit definition of a standard derivative. So if you'll recall, how did we define the derivative of a function? Well, we have some curve, say here, does something like this. We can say this is y equals f of x, y equals f of x, right? And how did we define the derivative? Well, we started by saying we want something that calculates rate of change, right? And we can calculate rate of change, an average rate of change between 2 points along the curve, right? We can take a secant line through these 2 points here, and we can calculate the slope of this line and get an average rate of change of the function over this interval, right? And how did we do that? Well, if this was the point f of x, say here we're at x, and the next point on the curve is f of x plus h, how did we find the average rate of change over this curve, right? Well, that was given by the difference, f of x plus h minus f of x, all over the linear distance that we spanned in the x direction, right? Which is x plus h minus x, which is just h, right? And so this gives us the slope of the secant line between these 2 points. But we want instantaneous rate of change, right? And so what that means is these 2 points, we want them to be arbitrarily close together so that we're really, instead of looking at a secant line, we're looking at a tangent line. So maybe in red here, or let's do blue. I'll draw the secant line here, right? But as these 2 points converge, or more so as x stays fixed and then x plus h shrinks to the point, then we would get a tangent line at x, right? And we found this by taking the limit as h goes to 0. And then the calculation of this limit gives us the slope of the tangent line. And so we said that this here, this was f prime of x. This is the instantaneous rate of change of the function y equals f of x at the point x, right? And so as x varies, the rate of change can vary, right? And we calculate the formulas for how the rate of change varies by computing the derivative. So why am I bringing up the single variable definition of the derivative when we're about to learn about partial derivatives? Because this notion here, this construction for finding this definition of the derivative is very much used in finding partial derivatives. So now we have some surface, say here. There's some surface given by, we know we can represent a surface by f of xy, right? By something like z equals f of xy. And let's give ourselves some orientation here. So we know, we'll say z is up, x is positive x is to the right, and then y is into the screen. So here's our coordinate system. So we kind of know what we're looking at here. And now we want to come up with definitions for partial derivatives, right? But so first, what do partial derivatives do? Well, if you notice, at any given point in the curve or on the surface here, you can look at a curve given by holding one variable constant. So if we hold y constant and vary x through this point, we get like a curve through here. And we could do the same thing and hold x constant and then take a curve through this y value, something like this, right? Here. And now what we want to do is ask the following question. We want to say, well, now what's the instantaneous rate of change in the x direction? And what's the instantaneous rate of change in the y direction? So we can take a tangent line approximation through this point, or take a tangent line to this curve where y is fixed, and look at the slope of this tangent line. The slope of this tangent line, so remember, again, here, this is the x direction, and this is the y direction, right? Or not. That's kind of a bad representation because y is going into the screen. I don't want you to think it's straight up, right? Like y is going, let's put it over here. There we go. So, and then what this slope here is, so slope of this tangent line is called the partial derivative with respect to x. So that WRT there is abbreviated, or it's abbreviation for with respect to. Okay. And so what we can do now is consider the same notion of the derivative where we're calculating instantaneous rate of change, but now we want it just along in the x direction, right? So what it's asking is, how is our surface behaving just in the x direction, right? How is it changing just in the x direction? And so maybe you can guess also that if you look at the slope of the tangent line to the curve where x was fixed and y is varying now, which is the second curve I've drawn, well, the slope of that tangent line is the partial derivative with respect to y, right? And notice when we take the partial derivative with respect to y, we fix the x coordinate, right? If you notice this line in green, or this curve in green, is at a fixed x value, right? X does not change. It is not moving left or right for us, right? And the red curve, or I'll use yellow here so it doesn't kind of get mixed in with the red tangent line. The yellow curve here is fixed in the y direction. It's not moving towards or away from us. And this is the partial derivative with respect to x, because the only thing that's varying on this yellow curve is the variable x. And the only thing that's varying in the green curve is the variable y, right? And so this is the geometric idea of what partial derivatives are calculating. It's calculating how is the surface behaving in each coordinate direction, right? Well, each coordinate direction in the domain, right? So if this was a function of 3 variables, we would say, how is the surface, or how is the hypersurface changing in the x direction? And that would be the partial derivative with respect to x. How is the surface changing in the y direction? That would be the partial derivative with respect to y. How's the surface changing in the z direction? Partial derivative with respect to z, right? And so now what we want to do is come up with limit definitions for partial derivatives. And so we will indicate, maybe I'll give us some notation here. So let's redraw our picture. Say our surface goes off the screen or something, right? And so we're looking at a point, and then we're going to see how is the surface changing in the x direction, right? At a fixed y value, how is the surface changing in the y direction with a fixed x value, right? And we said, okay, well, we'll take the slope of the tangent line to the curve when we fix y, and this was the partial derivative with respect to x. And notation for the partial derivative with respect to x is, you remember we would say the derivative of f with respect to x. We would say d dx, right? Or df dx. So this was single variable. You would say, or we would write like f prime of x, right? But now, in multivariable settings, we introduce a new symbol. The symbol is kind of a, maybe that's not the best calligraphy there. Kind of like a backwards 6 almost, right? And it has a name. The name of the symbol is a del, D-E-L. It's not a Greek letter or anything. It's just a symbol that mathematicians have made up. And it reads as partial. So when you want to describe the partial derivative with respect to x, you write partial of f partial x, right? Partial f partial x. This is the partial derivative with respect to x, okay? And so the partial derivative with respect to y, and so what would this be, right? Then the slope of this line here is what we would say is partial f partial x. Or sometimes people get lazy and sloppy and still just say df dx, right? So the slope here, not the slop, the slope, okay? And then what about the slope of the tangent line to the curve where x is fixed and y is varying, right? Something here. Well, the slope of this tangent line is the partial derivative of f with respect to y. So del f, del y, okay? And maybe some other notation here. Notice there's Leibniz notation, or Leibniz notation, which is this expressed as a, looks like a fraction, right? And then we have this kind of shorthand prime notation here. There is an analogous notation for partial derivatives as well, right? And so sometimes we'll use that quite often to save space and time when calculating partial derivatives. So we'll say the partial derivative of f with respect to x, we'll write that as f sub x of xy. This subscript here means to take the derivative of this function with respect to x, or the partial derivative of f with respect to y is f sub y xy, right? And then so this is all just notation, right? But geometrically what it is calculating still instantaneous rate of change, but in now just in coordinate directions, in each coordinate direction of our domain. And so now that we have this, let's get some rigorous definitions. Save me having to draw this again. Okay. So let's find a definition for the partial derivative of f with respect to x. Now, we do this the same by, let's first start with finding the average rate of change through a secant line, right? You take 2 points on the curve here, and we can call this the point xy, the first point here, and then what's the second point, right? Well, we want to vary x, and y is remaining unchanged, right? Y is constant here. And so we're going to look at an increased x value, but y remains unchanged, right? And rather, this is f of xy and f of x plus hy, right? And then so the average rate of change, or the slope of the secant line, is rise over run, right? And the rise over run is f of x plus h, or here, let's write this in black. F of x plus h comma y minus f of xy all over h. But now we want this h this x plus h to get arbitrarily close to f of xy. So we get an approximation for the slope of the tangent line there, right? And so we take the limit as h goes to 0. And this is our definition for the partial derivative of f with respect to x. It's the intuition is very similar to defining the derivative in the single variable case. And so how about df dy? Well, it's going to be very similar, and we'll call this, we'll say now, as k goes to 0, right? Now we want a secant line through the curve that has a fixed x value and varies in y. And so here we have, again, f of xy, and then somewhere down the line here we have f of x comma y plus k, because y is now what's varying. And so to find this, the average value of the secant line here, it's f of x y plus k minus f of xy all over h. And to get, or sorry, k. And to get the equation for the tangent line there, you send k to 0. You take the limit as k goes to 0, and then the slopes of these secant lines eventually give you the slope of the tangent line. And so these are the limit definitions of partial derivatives. Okay, so now that we have hopefully a good intuition and an understanding of these definitions, let's calculate some partial derivatives. So here's example 1. Let's find partial derivative of f with respect to x and partial derivative of f with respect to y of what function? Let's let f of xy be the function x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. Okay, and we want to find these partial derivatives. Well, right now, these these are our only definitions, is to calculate these limits. So let's do that. All right. So let's find, we'll say that, and so I can write this as f sub x of xy. Remember, this subscript x means to take the partial derivative with respect to x, right? So this is df dx, right? or del f del x. Now, it's going to be the limit as h approaches 0 of, let's go back to our definition, f of x plus h comma y. So what is f of x plus h comma y? Well, that's everywhere you see an x, you replace it with x plus h. So we have x plus h squared minus 3 times x plus h y plus 2y squared minus 4x plus h plus 5y minus 12. Now, this is f of xy plus h, right? And then we have minus f of xy. And then so we copy x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. And then all of this is over h, okay? And so now what we can do is basically factor everything out or FOIL everything and then simplify, right? So let's expand all of these parentheses here. So we have x plus h squared. Okay, so it looks like this is going to be, I may need a new page, but we'll see. If the limit is h goes to 0, and then I have x squared plus 2xh plus h squared minus 3xy minus 3yh, right? Because you have to distribute the 3 and you have to distribute the y. So, and then it looks like we're going to get plus 2y squared minus 4x minus 4h. And then we have plus 5y minus 12. Well, then if we factor, remember we have to factor this negative sign. We have to distribute that to every term, right, etc. So it looks like we're going to get minus x squared plus 3xy minus 2y squared plus 4x minus 5y plus 12. And remember, all of this is divided by h, right? So you can kind of see it in the corner here, right? It's all, everything in the parentheses here. This is all divided by h, okay? And now we can kind of simplify what we have. Right, there's a lot of terms here, and the kind of most natural place, for me at least, to go from here is to say, how can I simplify this, right? And so I look and say, okay, well, here's an x squared, here's a negative x squared. Here's a negative 3xy, here's a positive 3xy. Here's a plus 2y squared, here's a minus 2y squared. Here's a plus 4x, here's a minus 4x. Here's a plus 5y, here's a minus 5y. And then I have a minus 12 and I have a plus 12. And I think that's it for simplifying. So what's left? So we have 2xh plus h squared minus 3yh minus 4h over h, right? And so let's simplify this. So all of that is equal to the limit as h approaches 0, it was 2xh plus h squared minus 3hy minus 4h all over h. Well, now each term has an h in it, so we can simplify with the h in the denominator. This is limit as h goes to 0 of 2x plus h minus 3y minus 4, right? And now this is a simple enough expression that we can just take the limit as h goes to 0. Well, this function is defined at h equals 0, so we can just substitute 0 for h, and it looks like this limit is going to be 2x minus 3y minus 4. And so here is our this is df dx, which was the same as f sub x of xy, right? And so this is our partial derivative. Now, we also have df dy to calculate here. So let's do that. And I think what I'm going to do is, since the function is here, let's just reuse this page. Got to erase this. Okay. And so now, let's calculate the partial derivative with respect to y, which the other notation would be, say, f sub y, or the partial with respect to y. Now this is the limit, as we use k goes to 0, of f of x y plus h minus f of x y, or k, sorry, I keep wanting to use h, all over k. So this is the limit as k goes to 0. I'll start writing small immediately to try to save some room here. This is f of x, y plus k. So everywhere we see a y, we have to replace it with y plus k. So this is x squared minus 3xy plus k plus 2y plus k squared minus 4x plus 5y plus k minus 12. And now that's f of x, y plus k. And then that's minus f of xy. So x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. All of this is over k. Now let's do the same thing we did. Right now, what you do from here is you like multiply everything out, you distribute, you FOIL, etc., etc. You get it in as many terms as it can be, and then you cancel what you can, and then take the limit after that. So now we have, this is the limit as k goes to 0 of, we have x squared, and then it looks like we're going to have minus 3xy minus 3yk plus 2, and then so it's going to be, if you factor out the y plus k, you get y squared plus, so the y squared term multiplied by 2 is 2y squared, and then what's the next term? It's going to be 2yk, but it's 2yk times 2, so this is plus 4yk, and then plus 2k squared minus 4x plus 5y plus 5k minus 12. And then now we just distribute this negative again here to every term in the f of xy. So it's going to be minus x squared plus 3xy minus 2y squared plus 4x minus 5y plus 12, all over k, right? So a lot of terms. Let's see what cancels. I see a plus x squared, I see a minus x squared, so those cancel. I see a plus 3xy and I see a minus 3xy, so those cancel. I see a plus 2y squared minus 2y squared plus 4x minus 4x. Plus 5, whoops. Plus 5y minus 5y minus 12 plus 12. And I believe that's it. Yes. So what are we left with? We're left with negative 3yk plus 4yk, right? Did I? Sorry, this is, I made an error here. There, I'll point out my error in yellow. There's an x here that I did not distribute. I did in this term here, right? The negative 3xy, but here, this should not be a y. This should be an x. So this term should be minus 3xk. Sorry to all of you screaming at your computer that I was wrong there for a while. Okay. And so this looks a lot better now. And this is what we have left. We have negative 3xk plus 4yk plus 2k squared plus 5k all over k. So what we have, whoops, is the limit as k goes to 0 of, it was negative 3xk plus 4yk plus 2k squared plus 5k all over k. Okay? So then we can simplify a bit more since every term has a k in it. Limit as k goes to 0. Negative 3x plus 4y plus 2k plus 5. And evaluating this limit at k equals 0 gives us negative 3x plus 4y plus 5. And this is partial derivative of f with respect to y, which again, to emphasize the different notations, is f sub y. Whoops. F sub y of xy. Okay, and that was very tedious, right? The limit definition of a derivative is always a tedious calculation, even for relatively simple functions. So hopefully there's an easier way to do this, and there is, right? When we were learning about understanding partial derivatives, I was saying that, we pick a curve, like at a given point, you take a curve, and if you want the partial derivative with respect to x, it's a constant y value along this curve, right? And so what that means is along this curve, you can think of y as a constant and not a variable. And we can calculate partial derivatives using this idea. The idea now is that we can use our single variable derivative rules for calculating the slope or the instantaneous rate of change of this curve and just treat y as a constant. Say we just do differentiation in the x variable, but treat y as a constant, right? We still have to acknowledge its existence, but along this curve, it's fixed. And so we can think of it as a constant. And so here's how we can calculate partial derivatives. So to calculate partial derivatives, what we want to do is use derivative rules from single variable case and treat all other variables as constant. So when we want the partial derivative of f with respect to x, this means use rules. So let's say use derivative rules in x, treat y as constant. When you want df dy, or excuse me, del f del y, you want to use the derivative rules in y, treat x as constant, right? And if this was a function of 3 variables, it would be the same thing for del f del z. You would just use derivative rules in z and then treat the variables x and y as a constant. So let's do some examples. And let's use the same function here, right? So let's use this f of xy, the same one. So if we want del f del x using our new understanding of being able to treat other variables as constants, because essentially that's what we're doing geometrically. Well, this means this is the partial derivative with respect to x of x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12, right? What derivative rules do we know from single variable? Well, we know that the derivative it splits over addition and subtraction. So this is partial derivative with respect to x of x squared minus the partial derivative with respect to x of 3xy. And so, right, plus partial derivative with respect to x of 2y squared minus partial derivative with respect to x of 4x plus partial derivative with respect to x of 5y minus partial derivative with respect to x of 12, right? And so we'll get to the point where we don't have to write out partial x every single time, but to get the idea of using differentiation rules that we're used to, it's helpful to do this. And so now we take the derivative term by term, treating y as a constant because we're taking the derivative with respect to x. So we have the partial derivative with respect to x of x squared, right? Well, what's the derivative of x squared with respect to x? It's 2x. We have the partial derivative, so and then minus, right? Partial derivative with respect to x of 3xy. Well, if y is a constant, what derivative rules do we know? We know that you can kick a constant out front and then take the derivative of what's left, right? And y is a constant, so this is the same thing as 3y times the partial derivative with respect to x of x. And so the partial derivative here is then just 3y, right? Because the derivative of x is 1. So this is minus 3y. Here we have d dx, partial derivative with respect to x of 2y squared. This is a constant with respect to x. We are treating y as a constant, and the derivative of a constant is 0. So plus 0 minus derivative with respect to x of 4x, so minus 4. 5y is constant with respect to x, so its derivative is 0. And then 12 is a constant in any variable, and its derivative is 0, right? So it looks like our partial derivative is 2x minus 3y minus 4. And if you click back in the video and check what we got from the limit definition, you'll notice that this agrees with what we calculated using the limit definition. And so we can take partial derivatives using this. And notice this is a lot nicer, right? And so what if we want to find the partial derivative with respect to y? Well, we can do the same thing. Let's find del f del y. partial derivative of f with respect to y, right? And so now this is partial with respect to y, x squared minus 3xy plus 2y squared minus 4x plus 5, y minus 12, okay? And so let's, now we have our differentiation rules, but it's in the variable y instead of the variable x. Now, x is what we're treating as constant, right? This d dy says where y is varying, x is constant. And so this is a partial derivative with respect to y of x squared. We can use our derivative rule, our single variable derivative rules, but now in the variable y. So minus partial with respect to y, 3xy plus d dy 2y squared minus d dy 4x plus partial with respect to y, 5y, and then minus, so it's going to be d dy of negative 12, which is 0, right? So I'll just leave that term off here. Save some room. Okay, so I can write plus 0. Say we've already evaluated that last derivative. So now we're calculating the partial derivative with respect to y, and we'll go down the line here of each term. X is constant with respect to y, and so that means the derivative, and what we know the derivative of a constant is 0. So this is 0. And then we have minus. Well, we can use our rule that constants can be pulled out front before we take the derivative, right? And so 3x is a constant with respect to y. So this is the same as minus 3x d dy of y. And the derivative of y with respect to y is just 1, right? And so what we'll get is that the derivative of negative 3xy with respect to y is negative 3x. Plus, what's the derivative of 2y squared with respect to y? Well, there's no x's in here, so just standard power rule, 4y, minus the derivative with respect to y of 4x. That is a constant because we're treating x as a constant. So this is minus 0. And then we have plus the derivative with respect to y of 5y, which is plus 5, right? And so the partial derivative of the function with respect to y is negative 3x plus 4y plus 5. And again, if you go back, I don't think I saved it. Oh, there you go. I did save this one. You notice that the partial derivative with respect to y that we calculated using the limit definition is identical to how we calculated the partial derivative by treating y as a constant. And so now we know how to calculate partial derivatives. And this is a nice breaking point. I think where I'd like to go from here is maybe a little more difficult examples, and then we can start to talk about partial derivatives of higher order, so like second order partial derivatives. And then maybe, yeah, I think then from there, we can start to talk about how to find equations for tangent planes and linear approximations and things like that. So this will do it for this video. In the next one, we will discuss maybe some more difficult examples and higher order partial derivatives.